Same thing, I forgot to record with the video, so now I'm just do a cover up. So section 2.2 is going to talk about volumes. So when we're talking about volumes, we actually have three different methods. In section 2.2, we're going to talk about two methods, the disk method and then the washer method. This is the first part for the disk method. The example we have is we have a function f of x equal to 1 over x, which is the orange graph. And then we're going to revolving this shape along the x-axis to get a three-dimensional shape. And you can see that after the rotation, this is going to be a solid three-dimensional object. So what we're going to do, how are we going to find the volume? We're going to slice them. And in section 2.1, we use decimals. Decimal is a good tool to find the two-dimensional shape. But in 2.2 and 2.3, we're going to talk about three-dimensional volumes. So you still can use decimals as your support, but you have to imagine the three-dimensional graph. So how are we going to find this volume? We're going to slice it. Imagine that we have, really thin slice. The slice is even thinner than our hairs. It's really thin. And then we just pick one slice. And once we turn this slice facing to us, the slice is going to become to a circle disc. It's solid. So because it's a circle, we know how to find the area of this circle. So the area of a circle, which is pi r squared. So we need to find the r. It is easy to just talking about the r on the circle, but we have to associate with the original three-dimensional shape and also the original function f of x. So the radius on this circle is actually corresponded to the line on the original graph, which is the y value, the height of the graph. Depending on what is your x values, your height is going to be different, your y value is going to be different. So we're not going to thinking about y in terms of 1 or 2. We're actually going to thinking about y in terms of function. So that's why y is equal to 1 over x, which is going to be your radius. Now we got the radius, it's easy for us to find the area of this slice. However, we're going to slice the three-dimensional object infinitely many slices, and each one, even though it's really thin, we still imagine that there is a thickness. And this thickness is going to be dx. Now we can start to set it up for the volume. So the volume, we're talking about from the interval 1 to 2, so integral from 1 to 2. For one slice is going to be the area of a circle, which is pi r squared, where we already talked about the r is going to be the y for this case, which is 1 over x squared. Because even though one slice is really, really thin, we're still thinking about this as an object. So we're going to multiply by the thickness, which is the dx. So that is equal to pi r squared times dx. You can also thinking about that the dx and the integral symbol come together. And then you just have infinitely many areas and then summing up all those areas from x equal to 1 to 2. Either way is fine. You can thinking about dx as the thickness of the slice. You can also thinking about the dx is coming in pairs with the integral sign. Now this is the setup. And once we have the setup, we can start to finding the integral. Pi is a constant, we can put it out. And then 1 over x squared is going to be x to the negative second power. I like using the power versions because I can using the power rule. So x to the negative 2 becomes to x to the negative 2 plus 1 over negative 2 plus 1. And evaluate it at x equal to 1 to 2, which becomes to negative x to the negative 1 power, which is negative 1 over x. Evaluate from 1 to 2, which is negative 1 half minus 1, minus a negative 1, which is pi over 2. So the reason for us to call this is a disk method, because each slice, when we slice them, it is going to give us a nice circle, solid, there's nothing more, so just like a disk. That's why it's called a disk method, and then we were finding the area, or we were using the area of the circle way to finding the areas of each disk. The only thing we need to worry is what is the radius r. Now let's looking at another example where the function f of x is equal to square root of 4 minus x. From decimal, we can see the two-dimensional graph. We want an interval from 0 to 4, and so that's why it's only this much. And then we are going to rotate it along the x-axis. So the three-dimensional shape looks like that versions. And this is also solid because the region we're going to rotating is the region between the graph f of x and then the x-axis. So now if we slice one slice and turn it facing to us, we are going to get a circle. And this is a solid circle. The radius is going to be the height, which is going to be the y value. For this case, it's going to be square root of 4 minus x. Again, the radius r will change based on the x we're talking about. So for this particular x, we have a particular y value, but in general, the radius, or the y, is represented in terms of function square root of 4 minus x. So as the slice goes, our disk could be larger, could be smaller, so the radius could be larger, could be smaller too. So you can see that if I have 3 different slices, the radius is going to be different for different x value. But we can, using the function square root of 4 minus x, to representing all the radius. So now we're going to finding the volume from 0 to 4. So integral from 0 to 4 of the pi r square, pi times square root of 4 minus x, the quantity square, dx. And now we can integrate it, put the pi out because pi is a constant, and square root and square can cancel each other. We ending up with 4 minus x. The antiderivative is just 4x and x squared over 2. Evaluate at 0 to 4. We ended up with 16 pi minus 16 pi over 2, which is 8 pi. So those are the two examples. We're using dx as the way to set it up. Because we slice our single slice vertically, but we can also set it up in terms of dy, but it's not for the examples we had on the top, for a different problem. For example, here we have y equal to x cubed as the original function, and we're going to evaluate it from 0, or we want it from the interval 0 to 8. And then we're going to rotate it along the y-axis. And because of the shape, the three-dimensional shape we have here, when we slice them, we have to slice it horizontally. And because we slice them horizontally, once we turn on the shape, it's still going to be a circle disc, but this time the radius r is going to be here, which is corresponded to the x value. So that means the thickness of this slice is going to be dy. So we have to rewrite x in terms of a function y, which is a cube root of y. So the volume is going to integrate from 0 to 8 of pi r squared, but this time r is going to be x, and it's going to be dy. So in general speaking, if when you slice the object, the three-dimensional shape, if you slice them vertically, you are going to using dx. When you slice them horizontally, you are going to using dy.